So as Kara said, I'm going to be talking about characterizing polymers, both using a single detector method and moving from a single detector method to multi-detectors, both dual, triple, and quadruple detector size exclusion chromatography setup. So before I get started, basically we're here because we're learning about polymer characterization. And polymers are all over the place. They're in the cars that we drive, they're in our entertainment, in our packing materials, in our pharmaceuticals, in our paints. And they're even in our chromatography systems. Not to mention they're in our columns that we use. Our columns are packed with polymers. Our EcoSec GPC system has multiple different types of polymers within it. If you're looking at the tubing, if you're looking at the box itself, there's polymers are everywhere. And we're really interested in knowing how we can characterize them. And as we develop new polymers, we need to be able to characterize them because we need to be able to tell where we can use them, what industry can we use them, what in-use product can we use them in. So it's very important to be able to characterize them. Now, I say the polymers are everywhere, but and that we need to characterize them. But what qualities of these polymers do we need to, in fact, characterize? So there's four major characterization properties that I'm going to talk about today. And these are the major ones that are normally seen when you're talking about size exclusion chromatography. Now, obviously, it varies depending on what type of detectors you have, but these are the four characteristics I'm going to focus on. So the first is probably the one we're most familiar with, the molar mass. We want to characterize the molar mass of our polymers. We want to know how much, or if they're 1,000 grams per mole, are they 1,000,000 grams per mole, and how that affects our in-use properties. Now this is kind of, an example of this is something like polystyrene. We know the monomer, the single unit of polystyrene, is toxic, but at the same time, our coffee cups are made out of polystyrene. So something's going on between where we go from the monomer to the polymer to be able to use that in our coffee cups. So we need to characterize the molar mass to be able to know that, in fact, the polystyrene is suitable molar mass to be used for that in use. From molar mass, we can look at architecture. In general, polymers are usually classified in three different architectures. We have a random coil, a rigid rod, and a spherical shape. And these have to do with effect properties such as diffusion. An example of this is actually in the pharmaceutical industry. They tend to have the polymers or the particles within your drugs, we want them to be spherical because the body tends to see non-spherical objects as foreign entities. So it's important to be able to dictate, is that shape in fact spherical, or has it become ellipsoidal where the body is not going to interact with the body the way that it's meant to be. The next one I'm going to have is branching. Branching tends to be based in two different categories. We have long chain branching and short chain branching. The difference between these two is the length of the branch compared to the polymeric backbone. This affects things as shear strength, crystallinity. We're going to talk about it in the terms of how it affects the intrinsic viscosity of our samples. But in general, this is something that, depending on your polymer, you may want to be able to characterize. The final one is polymeric size. The size is a relative term in polymer chemistry, and I'm going to talk about the various sizes later on in my talk through the examples. But in general, it affects, the most important thing that we're looking at usually is packing. The size affects how well we can pack our chromatography columns. We look at different particle sizes within our columns to see how many of those particles we can fit in there. Being in Florida, it's actually, if you want to go back to the real world, it's the typical orange growth problem. How many oranges can the orange picker put in a box? Depends on the size of the oranges. We can relate that back to polymer science. In paints, it actually affects the texture of paints. So as you can see, these four characteristics are affecting the in-use properties of all of our polymers. So we want to be able to characterize our polymers the most accurately and precise way possible, as well as get the most complete picture of our polymers. Because maybe molar mass tells us one thing, architecture tells us another, and we may need to combine those properties together in order to get the most information. So now that I told you how we can actually characterize them, we're going to talk about how we can use size exclusion chromatography with various detection methods to obtain these characteristics. So just a brief review. I just don't want to assume that everybody's familiar with SEC, but basically when we have size exclusion chromatography, we have a column, and our column is packed with a porous material. And we're separating our analytes based on size. So if we have a mixture of analytes, we inject a plug onto our column, and we have 3 analytes, a larger polymer, a medium-sized polymer in green, and a smaller polymer in purple. As the sample plug migrates through the column, the larger polymers are going to elute prior to the medium ones, prior to the smaller ones. They're going to sample less pore volume. Remember, the packing material has pores in it, so the larger particles are not going to be able to enter as many pores as the smallest particles, and so they will take a shorter path to exit the column, and they'll elute first. So if we look at a chromatogram that results from our size exclusion analysis, we'll have the retention time and a detector response, and while our larger particles will elute first, then our medium, and then our smallest. Now it's important, just like the name says, size exclusion chromatography. We separate based on size, or what's known as hydrodynamic volume, not molar mass. And remembering that's going to come into play in one of the examples that I'm going to show you later. But it's a lot of times people think, oh, I'm separating based on molar mass. It's just because something has a high molar mass doesn't mean it's necessarily the largest size polymer in your or in your sample. So you want to make sure that you realize that you are separating based on size. So to characterize those 4 properties that I was telling you about, we're going to take our SEC column and we're going to couple it to different detection methods. So like I said, they're probably most familiar with characterizing a polymer based on its molar mass. There's 2 ways to do this. The most traditional way, and probably the most practiced way in a QC type lab, dealing with polymers that are continuously made, that you're just trying to make sure they're the correct molar mass before you put them into the processing of your end product, is using a calibration curve. And this basically means you need one detector. You need some type of concentration detector. It can either be an RI detector, differential refractometer, or a UV detector. In general, RI detector tends to be more universal detector because your polymer must have a UV absorbing material in it in order to use your UV detector. So it's more specialized polymer, or you need a more specific polymer. Your polymer needs a more specific function to use your UV detector. Now, molar mass can also be determined a different way. We can use our same concentration sensitive detector in conjunction with a multi-angular light scattering detector to get what we say is the absolute molar mass of our sample. And when we're talking up here about either of these detectors, everything's calibration relative. So if I determine the molar mass of polymer X, it's relative to, say, polystyrene, which is what I made my calibration curve out of. When we go down here, the molar mass now becomes independent of any type of calibrant and solvent and temperature conditions. So it's what we say the absolute molar mass. And like I said, this is the multi-angular light scattering detector. It can have anywhere from 2, 3, 7, 18 angles are the ones typically used. And it measures the intensity of scattered light at those angles. And from there, at each slice eluting from your chromatography column, is matched up with the concentration at that given slice, and you obtain an absolute molar mass of your sample. So for molar mass, we want to go to the architecture. Now, this either requires you to have one of 2 types of triple detector systems. When we're talking about architecture a lot, we're looking at dimensionless ratios. And so you need to be able to have a numerator and a denominator from 2 separate detectors. So here, we can either have our multi-angular light scattering detector that I mentioned earlier with a viscometer, a differential viscometer, which measures the intrinsic viscosity of your sample, and from there you can obtain other information from calculations, and you'll need a differential refractive index detector. Now, the other option is to not have a viscometer and to have a multi-angular light scattering detector. And if you have a 18 angle detector, you can actually replace one of the photodiodes within here with what's known as a quasi-elastic light scattering detector. It's a different type of photodiode, and it actually results in measuring a different type of polymeric size, which will result into a different architecture ratio. As far as branching goes, you're going to be talking about the same type of detector system. You either need to have a viscometer or multi-angle light scattering detector coupled to a differential refractive index detector. So one or the other. So as you can see, kind of once you start adding in more than one detector, there's more information. So if you simply had an RI detector and then you added a multi-angle light scattering detector, we're already able to obtain both architecture and branching information for the characterization of our polymer. Finally, I didn't put any of the detectors down here because the three major ones three major ones we've been talking about, besides the concentration sensitive detector, which was our RI detector, can all be used to find different information about polymeric size. Now, in polymer chemistry, we typically have 4 radii we look at. We can determine. 3 of them we can determine using an online analysis, meaning using a separation method coupled to those detection methods. And they're basically a way of thinking about a polymer. So think about it this way. Everything is relative to the definition. If I'm in this room, standing here, I'm probably considered fairly short. I'm guessing a lot of you guys are taller than me. If I'm in a room full of kindergartners, I'm probably considered fairly tall. So if you want to make that type of comparison, it just depends on what you're comparing your polymer to and what the definition is. So the 3 radii, and I will define them in more detail later as we talk about examples, but there are the multi-angle light scattering detector. We get what's called the radius of gyration. The Quell's detector, the quasi-elastic or dynamic light scattering detector, is the hydrodynamic radius. This is also known to biochemists as the Stokes radius. And then by a combination of the viscometer with the moles and of course the DRI, and you're talking about the viscometric radius. So as you can see, as we add more detectors, we obtain a lot more information, but it's being able to extract all of that information from your chromatograms and from your data and put it all together in a way that can fully characterize your polymer. So let's start with what you're probably most familiar with, single detector SEC. Like I said, everything tends to be calibrant relative. If you look here, I have a SEC system. This is the EcoSec GPC system that TOSO sells, but basically what we need here is we need a pump, we need an auto injector, we need a concentration detector, we need SEC columns. The EcoSec, here we have the RI detector and the UV detector. I should note that the RI detector in the EcoSec is different than traditional RI detectors. It's a dual flow system, making the baseline a lot more stable than a traditional system. But if you have some more questions about that, I'll be glad to answer them later. But for right now, I want to show you that we have the 2 detectors. We can use them simultaneously, separate. For the sake of this, let's say we're just using the RI detector to monitor our chromatography and to determine our molar mass. So just like any chromatography, we obtain a chromatogram. Here we have the retention time on the x-axis and the RI detector response. Remember, we're doing size exclusion chromatography, so we're separating based on size. Larger analytes, smaller analytes. This is a polymer that we have, and so we have a pictorial picture of it. We have a picture of it and pictorial information, but how are we going to get quantitative information out of this? So we know from our columns they all have an ideal range of separation, an ideal size range, which is usually the separation range we talk about. And we know that each column also has an exclusion limit and a permeation limit. And we make what we call a calibration curve to determine the molar mass. So what we do is we usually inject standards onto our system of a known molar mass. Usually these are polystyrene, PMMA when we're dealing with organic eluents, PEO, PGs, and polyolans when we're dealing with aqueous eluents. And so we inject those onto our system, and they each have a retention volume. We correspond that retention time in the log of the molar mass to obtain a calibration curve. Then once we have our calibration curve, which would look something like this with the total permeation and the total exclusion limits on the 2 extremes where we're no longer in the linear region of our curve, we take our raw data from our sample, so we inject polymer X, and we take each slice along the chromatogram and we match it up with its corresponding retention volume on our calibration curve, and from there we can move over and get a molar mass. So we tend to look at this and obtain a molar mass distribution. And molar mass we look at in three different ways. We look at it in terms of the number average molar mass, the weight average molar mass, and the Z average molar mass. These are simply statistical moments. This is just telling us the distribution of the molar mass. Is our sample all of the same molar mass? Does it have some higher components, some lower components? What's the average molar mass? Things like that. We want to get a complete picture of our polymer. This also gives us an indication about the polydispersity of our polymer. And when I say that, I mean, is our polymer all of one molar mass or different molar masses? And again, the polydispersity of a polymer can affect the end use of our polymer. So some of the benefits of a single detector system. Out of everything I'm going to talk about today, it's probably the simplest to set up. One detector that most people are familiar with, an RI detector, a UV detector. We learned about UV detectors back in probably high school, so it's something that more people are familiar with. It has the best precision. As we add more detectors, our variances are additive, so the precision of our measurements is going to decrease. It's also, so that makes it great for day-to-day reproducibility. If I have polymer X, I should be able to run it on my EcoSec in our lab in Pennsylvania. Japan should be able to run it on theirs, and Germany should be able to run it on theirs. And as long as we have the same columns, the same experimental conditions, the same polymer we're analyzing, we should get the same answers. It also can be used for fractionation. Sometimes people just want to be able to separate a contaminant from their polymer of interest. It can be used in that terms. However, like I said, everything is calibrant relative, meaning when you report these values, you say, my value for polymer A, B, and C are based on a polystyrene calibration curve. Sometimes it's not the most accurate way to measure the molar mass of a polymer because the calibration curves for a polymer can change as the architecture and the chemistry of a polymer changes. So if you see here, if all three of these curves were of the same chemistry, they're actually of different architectures, so the curves vary. So your calibration curve can change depending on the architecture of your sample. And ideally, to get the most accurate information out of your calibration curve is going to be to take polystyrene, make polystyrene calibration curve, and measure polystyrene because it's the same chemistry, and make sure it's both linear polystyrene, the same architecture. So that's what I mean while it's a relative molar mass. It also has limited information. I had those 4 characteristics I wanted to look at. The only thing I can really obtain using this single detector is going to be the molar mass and the molar mass distribution. I'm not going to obtain any information about size or architecture or branching for my polymer. So why should we move to a multi-detector setup? Well, first of all, it's fairly easy in your lab to move from a single detector to a multi-detector setup. In our lab, we have the EcoSec with our 2 detectors that are housed within the unit, and then we've simply added 2 external detectors. You can add as many external detectors as you want. We have a light scattering detector and a viscometer. You can add an FTIR, you can add anything that you want onto to the back end of the system. The thing in our setup here, and the most important, is to make sure the RI cell can handle the back pressure of the system. So ideally, you'd like the RI detector to be last, but some cases that's not going to be able to obtain, such as if you have FTIR and it's a destructive technique, you want that to be the last detector on your system. So you just have to make sure that you're not going to blow the cells inside your RI detector. With our multi-detector chromatography setup, we can look at the absolute molar mass that I spoke about briefly when I talked about the Mols detector. We can look at copolymer composition. We get a very detailed picture that includes architecture, size, structure, branching, intrinsic viscosity, the composition, chemical heterogeneity. There's a laundry list of things we can look at here by adding these external detectors. So I'm actually going to talk about 3 examples now, 1 with a dual detector setup and 2 with a quadruple detector setup. So So the dual detector setup, we have an option of looking at copolymers and being able to analyze both the molar mass using calibration curves and using the two concentration detectors for chemical composition. So in general here, I have two different copolymers. So by copolymer, I simply mean that there's two different monomers present. Here I'm going to be talking about styrene and PMMA, so polystyrene, polymethyl methacrylate copolymers. And the two pictures that are dictated here just show that copolymers, there's different types. There's alternating copolymers, there's block copolymers, random copolymers. All of those can be used for this type of analysis, and we want to know how is the copolymer varying. So what is the percentage of A and B within our copolymer as maybe a function of the molar mass distribution. So what we do is we use both of our concentration sensitive detectors, and so just to review, we have the UV detector, and we know the UV detector signal is proportional to the molar absorptivity, the path length, and the concentration. We have our refractive index detector, and we know its signal is proportional to the concentration times the DNDC. And I don't know how many people DNDC is a new term for. Basically what you can do is you can think of the DNDC as the RI equivalent to the molar absorptivity. So it's a factor that you determined previously, and it acts the same way as the molar absorptivity term, but for the RI detector. So we have our two monomers. We have polystyrene and polymethyl methacrylate. Polystyrene is UV visible, while PMMA is not. So we have two concentration sensitive detectors. The UV detector is only going to detect the concentration of polystyrene, here in red, and then the RI detector is going to be able to detect the concentration of the whole entire sample. So the PMMA components and the polystyrene components. So this is just showing you with the retention volume, we have our two peaks eluting from our chromatography columns and the detector response. The blue is the RI, which is both components. The red is the UV, which is only the polystyrene because the other component cannot be detected in the UV detector. Now from there, how do we get the composition? We're basically interested in looking at the ratios of the two detectors across solution profile. Now let's be careful. I jumped to this picture and the axes are totally different and we're looking at different things from the raw data. So here we have the log, and this is a different sample. The other one was just showing you what we're getting. So this is actually a real sample here. So this is a sample with polystyrene and PMMA, and here we've gone we have the log of the molar mass on the x-axis, and we've gone from raw data in a detector response to the differential distribution of the sample, okay? And so everything here is so-called been normalized, brought on a scale. That's why the two peaks are basically overlapping one another. But what I wanted to show you is how we can get the molar mass. We look at the molar mass distribution, and at the same time, we can look at the copolymer composition across the distribution. So for this particular example, you can see the copolymer composition is about 30% of the copolymer for the copolymer. So by just having these two concentration sensitive detectors, you can obtain more information about your polymer if you're dealing with a copolymer than if you only had one detector. So now I'm going to look at multi-detector techniques. So a little background on this sample. The sample I'm going to it's called an Inovasphere. It's from Innovation Laboratories. This is a collaboration that I did with them. They have developed this technology as a drug delivery vesicle or something environmental that can move a fluorophore from one location to the next. Basically what it is you're looking at a particle with a polymeric shell and a void volume in the middle. The volume in the middle can be used to house a drug, can use a multiplicity of things depending on the end use. They've developed this, it's in an aqueous eluent, so if you differentiate between GPC and GFC, we're moving to GFC here, and so we're dealing with aqueous. And they've been able to characterize this using transmission electron microscopy, and that's what you see here. And if you look closely, I don't know how well you guys can see the pictures, but the ones that I have circled over here, you can see the size and shape isn't very consistent. It seems to vary. Now I should also say if this wants to be used for drug delivery, the best way to characterize a sample is in the environment most similar to its end use. So when you do TEM, you're doing it under vacuum. Probably your body, or when you put it into your body's not under vacuum. So ideally you'd like to be able to analyze this in aqueous conditions, because sometimes the shape and the size may change when you analyze something in vacuum or a different solvent, from things like that. So just note that we're actually trying to use or analyze this in the most common condition for its end use. So when we have a multi-detector setup, I'm talking about having a multi-angle light scattering detector, quasi-elastic light scattering detector, a differential refractive index detector, and a differential viscometer. We tend to disconnect our light scattering detector from our SEC system and do offline analysis. Now, a lot of people skip this step. Why is this important? Offline analysis allows you to analyze the molar mass and the radius of your sample without any separation, which lets you get the bulk properties. At the same time, it also lets you see, is your sample experiencing on-column flow-induced degradation? Is your sample aggregating on your column? Is your sample sticking to your column? Or is something occurring because of the column and the column packing material affecting the results that you're obtaining at the end? So we disconnect our system from SEC and we get offline analysis. And you see here we have the molecular weight and the radius of gyration for offline analysis. Then we set our system all back up and we do online analysis. This value is for 1 milliminute. I tend to run things if I'm unsure of the polymer at multiple flow rates, especially when their molar mass is so high, to make sure in fact I'm not degrading my polymer because of the columns and the pores within my SEC column. But I'll tell you, this is at three different flow rates. I ran this out, I got the same values. So I'll save you that explanation, or save you all of that data, and just show you that the importance here is that the offline values and the online values differ greatly from one another. So that when this occurs, that brings us back to the drawing board. What is going on with our sample? The molar mass is decreasing significantly online, changing flow rate to lower flow rate, didn't make a change in it, probably not degrading it. So what's occurring? Well, the first thing, go back to the chromatogram. This is the bulk of why you're doing this, right? You're doing a separation. You're trying to separate the size of your molecule or particle or analyte that you're looking at. So we went back to the drawing board, to our chromatogram, the first part of information that we can obtain data from. So I have the retention volume on the x-axis. I should say this is all at 1 milliminute, so the volume and if it was retention time would be the same. And this is the 90-degree light scattering detector. This is just the photodiode at that angle for the detector. And so we've plotted the chromatogram. So this is what's occurring, and we came up, there's 2 peaks. We were expecting one thing. I told you I just had an Inovasphere. I just had this one sample. Well, turns out I have more than this one sample. I have 2 things going on, and that's why my offline values are so much higher, because this one peak here is my actual sample, and this peak here is something I wasn't expecting. It's eluting prior to my sample, so it's bigger, but what do I know about it? And this is where the benefit having multiple detectors comes in. From here, we went from just looking at the light scattering signal to looking at the refractive index signal. We have a concentration sensitive detector. We have all of these detectors. We might as well use them together to see if we can tell a story. So here in blue, and I'm not sure if you can see a difference between the blue and black, but here in blue we have the RI signal. Now the RI is roughly proportional to just concentration. And if you notice, this is just a flat line. And I should back up and say I'm just looking at this portion of the chromatogram right now, the 12 to 13 milliliter portion. The light scattering signal in general is proportional to molar mass times the concentration. We already know this portion of our chromatogram is at a very low concentration, so in order to get a detector response from our light scattering signal, it has to be very high in molar mass. And in fact it is. This, I'm going to call it a contaminant now. This contaminant, or whatever it is in this sample, is actually about 200 plus nanometers in size. So it's extremely large compared to the actual sample itself. This is also, I don't know, this probably won't mean anything if you're not that familiar with light scattering, but basically in our light scattering detector we measure multiple angles. The larger our particles, the bigger variation of scattering in the different angles we see. So this is the contaminant, and you can see each of these angles varies from one another, the amount of scattered light, while the Inovasphere peak is fairly close to one another, so because it's a smaller analyte. But the point within this is that when I was showing you the TEM, we couldn't see this. We had no idea this was present because it was at such low concentrations. So when we move to use from a TEM type measurement to a size exclusion measurement or chromatography measurement, we can actually obtain more information about this sample. This is also helpful for the company in the fact that they need to be able to get rid of this or identify this if it ever wants to be used for drug delivery or something like that. They have to be able to identify every portion of what's present in their analyte. Now I'm going to talk about the size of this particle. So let me step back for 1 second. Just make sure from now on we're just talking about this big peak. The peak from 13 to about 15 milliliters. I'm going to ignore this so-called contaminant peak. So we're going to look at the size. Now I mentioned we have multiple sizes in polymer science. So the two that we're going to focus on for this particular example are the ones obtained from the two light scattering detectors, the multi-angular light scattering detector and the quasi-elastic light scattering detector. So these are RG, or the radius of gyration, and the hydrodynamic radius. And so by definition, the radius of gyration is the root mean square distance of an array of atoms from their common center of mass. And for the hydrodynamic radius, or Stokes radius, that's the radius of an equivalent hard sphere that has the same translational diffusion coefficient as a similar macromolecule. So those are just the definitions of the two radii that I'm going to talk about. So here are those radii plotted as a function of retention volume. So on the x-axis, we have the retention volume. First y-axis, this is the 90-degree light scattering signal, which is the actual chromatogram. And again, we could plot any of the detectors, but I just chose to plot the light scattering detector. And over here we have the radius. We have the radius and gyration in blue and the hydrodynamic radius in red. And you can see here we're eluting based on size, so we should have the larger portion of our analyte eluting prior to our smaller ones. And again, we don't expect these to be the same because they're relative terms. So we can just see that the radius varies from about 30 to 15 nanometers depending on which one you're looking at. Important here though is it tells us that our sample is polydispersed with respect to radius. If our sample of everything was of the same radius, so let's say everything was 25 nanometers, we would expect a straight line going across our elution profile at 25 nanometers. So the size of this particle polymer is definitely changing. It's not uniform for the whole sample. Now let's step back a minute for traditional SEC when we're talking about calibration curves. Remember, we're separating based on size, larger eluents, smaller eluents. We make our calibration curves assuming that the eluents that are larger are going to have a larger molar mass. The eluents that are smaller are going to have a smaller molar mass. So if we took a calibration curve, we could, as far as molar mass and radius, I was trying to show you that we would expect larger radius, higher molar mass, the molar mass to decrease as a function of increasing elution volume. If we were typically using a calibration curve, this is what we would expect. Now remember, we're doing multi-angular light scattering here. And so I'm going to show you, here's the molar mass plot for the Inovasphere. It's got the opposite trend as we're traditionally used to. We're used to the molar mass decreasing as a function of increasing elution volume. For this particular example, our molar mass is increasing as a function of increasing elution volume. So if we're separating based on size, our larger analytes are over here with the lower molar mass. Our smaller analytes are over here with the higher molar mass. Not really what we traditionally expect, and I'm going to kind of explain this more as we move from on. I'm going to go to the architecture and then come back to using the architecture, the molar mass, and the size to get a very complete picture of this. But this is an example where traditional single detector SEC would have given us incorrect results. So with the architecture, I mentioned that we look at dimensionless ratios when we talk about the architecture. So here we're looking at the ratio of the size determined from the multi-angle light scattering detector and that of the quasi-elastic light scattering detector. Now these are two independent measurements. The two light scattering detectors they're independent from one another in the data they obtain. So we're looking at the ratio of Rg to Rh, and this is known as the rho value, and this provides information about the shape. If you go and look into the literature, you'll find values for hard spheres, soft spheres, prolate and oblate ellipsoidal particles. This intermediate sphere is something between the two, if you want a definition or be able to differentiate between the two. Hard sphere is like something very compact, like a baseball. Soft sphere is something more like a foam ball. And I like to think of intermediate sphere maybe if something consistency of as like a Nerf ball or something like that. So for this particular sample, the rho value ranges from 0.89 to 1.37. And that's somewhere between an intermediate sphere and a prolate ellipsoid. And if we look at that in conjunction with the molar mass and the elution profile, we see that this sample, the ones that are lower in molar mass, have a more prolate ellipsoidal shape than those that are higher in molar mass, which have a more spherical shape. If you move even further and compare that to the radius, we see that the larger portion of this polymer, the larger radius, is a lower molar mass, more ellipsoidal shaped. The smaller radius is a higher molar mass and a more compact spherical shape. So let's say this whole analysis, one run, it's about 15 minutes. I ran at 1 mil a minute, so about 15 minutes. In 15 minutes, with all of these detectors, I just provided you a very complete picture of this polymer. I showed you there was a contaminant. I showed you how the size changed. I showed you how the molar mass changed, how the structure changed. And so it shows you that multi-detector SEC or any type of multi-detector chromatography can provide you with a much more complete picture than your single detector system. I have one last example, and this is basically, I want to show you how you can use the viscometer. I didn't talk about the viscometer in the last example. It was on that system, but this is actually a better example on how the viscometer can tell you more information. So this is a sample called Ultranan. It's an ultra-high molar mass polysaccharide. This is from a collaboration with the Greg Cote's lab at the USDA. They produced this Ultranan from bacteria. They know it has a huge molar mass. Their idea is to replace it as a possible domestic replacement for gum arabic, obviously to lower the cost. Gum arabic tends to be used as a non-caloric food additive in paints, things like that. So it's something they're trying to make to use for an in-use, and they need to be able to characterize it. So just like I mentioned before, we do offline analysis first. So offline analysis has a molar mass around 5 times 10 to the 7th. It's a pretty big polymer as far as molar mass goes, and the radius is about 57, according to offline analysis. Now remember, offline analysis has no type of separation. Then moves to online analysis. We started off at 1 mil a minute. The first thing we noticed, there's a big difference in the molar mass, big difference in the radius. What's occurring? Down to 0.2 mils a minute. We still have a fairly big difference in the two techniques. We actually went all the way down to 0.05 mils a minute and had the same results as 0.2 mils a minute. And at this point, these experiments were taking 6 hours. And we knew we were degrading our polymer. Our SEC columns had the biggest pore size, the biggest particle size possible, but we were still degrading it. This Ultranan was breaking in our columns, basically by on-column flow-induced degradation. Now I'm going to save you the time and the energy and just tell you that, because I want to talk about the viscometer, I don't want to talk about the molar mass or the radius for this sample. But from here we actually moved to a different technique known as hydrodynamic chromatography, and we stopped degrading our sample. So just so you know, we have this sample of a really high molar mass. We expect that it's a very high molar mass, seems to have a fairly small radius. It's expected that it has a lot of branching with those alpha 1,4, alpha 1,6 units. alpha 1 3, alpha 1 6 units. And so what we wanted to do is use our detectors. What can we get from the viscometer? So in general, the viscometer gets the intrinsic viscosity. You can think of this as an inverse density. It has the units that are inverse of density, milliliters per gram. And it's about, by definition, it's the amount of dissolved molecule contributes to the overall viscosity of the solution. The best way to think of this is if I had two beakers, both with water in it, and I added flour to one beaker, it's going to increase the viscosity. To the other beaker, I want to add some type of spherical molecule or particle to it to increase the viscosity the same amount. So we're just looking about how does that flour compare to the size of whatever spherical object I had to add to my other beaker. So we're going to use this to look at long chain branching. So what we did is we took our alternan, we ran it through our viscometer in our multi-detector setup, and we also went into our lab and we found Polymer. It has a very similar linkage that we could use it for a comparison to alternan, and we also know it's linear. Now, in our lab, we wanted to compare both the intrinsic viscosity and the viscometric radius. And so like I said, I kind of gave you the idea of what the viscometric radius was a second ago, but we're basically talking about that flour example. How are we changing the viscosity relative to a spherical object? So the best we could do in comparing the alternan to the Polymer was over an order of magnitude difference. And we saw that experimentally that the intrinsic viscosity for this alternan was about 300 times less than Polymer. Mind you, there's still a big molar mass difference here, and you can see molar mass goes into all these equations, but the radius was the same. So we said, well, we need a little more. So theoretically, we determined what the intrinsic viscosity and the viscometric radius of a Polymer that was roughly around the same as the alternan that we were talking about. So we used the Markowitz coefficients for the same solvent temperature conditions and calculated that if we had a Polymer, which mind you is linear, if it had the same molar mass of our alternan, it should have an intrinsic viscosity around 4,300 milliliters per gram compared to our 11 milliliters per gram. It also showed us that we should have a radius of 344 instead of a radius of 44. So by comparing a molecule that we know is linear to alternan, which we were expecting to be more compact and along the long chain branching, we can confirm that there's a very highly compact structure in this alternan. So this is just to show you the information that the viscometer can tell you and how it may help you form a more complete picture of not only the structure but the branching of your polymer. So just to conclude, we talked about single-detector SEC, dual-detector SEC, and multi-detector SEC. Single-detector is the most precise and reliable method. Like I said, as you increase detection methods, the variances are additive, so the precision is going to be decreasing. All of these methods we can use to determine molar mass. Single detector, we're looking at a calibration curve relative molar mass, while when we go to multi-detector, we're looking at the absolute molar mass. We talked about dual detector for copolymer analysis and looking at the percent composition of a copolymer, and then as I concluded with the examples for multi-detector SEC, we really do get a complete picture of our polymer with size, shape, architecture, molar mass, branching, things like that. All of this can be obtained in our setup. So you can see how much more information by adding those detectors you can obtain and increase your knowledge of the polymer and increase what you can characterize, which becomes very important when you're talking about making a new polymer. You want to know as much about it as possible.